Alright guys, I'll go through your study guide with you here. So if you need some help, feel free to check out the ones you need help with. Beginning problems. We did these in class already, but if you were absent, I can show you how to do them here. Basically, you have to recognize that what we're looking at here is the limit definition of a derivative. So you have to be able to identify two things, what your function is and what your c value is. The function is tangent. Comes from here. This is your x value. And the h you just kind of ignore. So the original function was tangent of x. The c value is just the x value that we're plugging in, which in this case is the pi over 6. Alright, so since this really just represents f prime of pi over 6, then what I need to do is I need to take the derivative of my function and plug in the pi over 6. Okay, secant of pi over 6 is 2 over radical 3, or some people write it as, let's see, 2 radical 3 over 3, but I'm just going to write it like this. Then you square it and you end up with 4/3 as your final answer. Alright, next question. This is the alternative form of the limit definition of a derivative. In this case, the function is even easier to identify because it doesn't have the h in there. So there's my function. The value you're trying to find the derivative at is this number here. So that would be 2 pi over 3. So this limit basically represents the derivative of f of x at 2 pi over 3. The derivative of f of x is cosine, and cosine of 2 pi over 3 is negative half. That's the answer for that one. Let's go ahead and move on. This one, we're back to the standard definition, limit definition of a derivative. This is an x. We ignore this, so the function is x to the 5th. The c value is the number that takes the place of the x there, which is 2/3. And so we're looking for f prime of 2/3. The derivative of x to the 5th is 5x to the 4th. And we're going to be plugging in 2/3 into that. 2/3 to the 4th power. You raise 2 to the 4th power, you get 16. You raise 3 to the 4th power, you get 81. Multiply that by 5 and you get 80 over 81. And that's that one. Moving along, we have this one. For this one, we have another alternative form limit definition of a derivative. So there's my function, there's my c value. So this is going to be equal to f prime of 4. Since my f of x is the square root of x, then the derivative of f of x, as you guys hopefully know, would be this. And since we're plugging in 4 for the x, we get that, which is 1/4. There's a lot going on in this problem. We need to determine if it is continuous or differentiable at each of the values indicated. So for number 5, we're trying to see is it continuous and differentiable at x equals 4. So to do that, we're going to limit as x approaches -4 from the left of the function. We want to verify that it does in fact equal the limit of the function as I approach 4 from the right, -4. So if I'm approaching -4 from the left, then I would be using this piece. And if I'm approaching 4 from the right, I would be using this piece. Direct substitution tells me that -4 is on this side, -4 is on this side, and they are in fact equal. And therefore it checks that this is continuous. So we'll say that it is continuous since the limit as x approaches 2 exists. And it would actually just give us the same thing if we just plug 2 into the original function, which is basically just plugging 4 into that piece there, so it's continuous. Now we want to see if it's differentiable. For a function to be differentiable, then we're going to do the same thing, but with the derivative. So the derivative of the top piece is -1, the derivative of the next one is 1, the derivative of 1 after that is -1/2, and the derivative of this next one is kind of interesting. I'll show my work on another page here. Okay, so when I take the derivative of this expression here with respect to x, the constant's not going to change, so that just stays there. But the derivative of cosine is negative sine. And I'm going to put the negative in the front. I don't want to put it in here. It'll make it look like subtraction. Then we don't want to forget to do our chain rule, the derivative of the inside also. And so these cancel out, and you're left with this. Okay. All right, so to determine if it's differentiable, we're going to do the same thing, but we're going to be doing it with the derivative. So I'm going to approach -4 from the left, and I'm going to approach -4 from the right, but this time I'm going to do it with the derivative functions. And we want to know, do they come out equal or not? So if I'm approaching -4 from the left, then I would be using the top, this top piece down here. And if I'm approaching -4 from the right, we would be using the next piece here. Since these are just numbers, there's nowhere to plug the x in. That's what the limits are. And those are not equal to each other. And so it's not differentiable. It is asking you guys to give an explanation as to why. And so this would be the explanation as to why. So it is continuous because of this, but it's not differentiable because of that. Okay? All right. Move on to the next question here. Matter of fact, let me bring all that back. There it is. All right. Rewrite the first part again. Okay, so for the next question, we're looking, is it differentiable at -2 this time? So we're going to go ahead and repeat this process, but this time we're approaching -2 from the left and right. Okay, so if I'm approaching -2 from the left of my original function to determine if it's continuous, -2 is here, and that's to the left of it, so that would be this piece. And if I'm approaching -2 from the right, that means x is greater than -2, which means I'd be using this piece. Okay, and we want to know, are these actually equal? So direct substitution here gives me -2, and direct substitution here Negative 2 squared is 4, and 4 times negative 1/4 is negative 1, and negative 1 take away 1 is negative 2. So, once again, it is continuous. Over here, differentiable. I'm approaching negative 2 from the left of the derivative. That would go with this second piece, just like on the last one we did. Positive one. And then if I'm approaching negative 2 from the right, I'm going to use this piece. Direct sub here gives me 1. Direct sub here gives me 1. Those are equal. So in this case, we're going to say, yes, it's differentiable. Since the limit as I approach negative 2 exists, and therefore that's what the derivative would equal at that point as well. So, that one. Okay, next question. And the next one we're going to be approaching a positive 2. Bring it up here real quick. Yep. So we're approaching positive 2 next. So we're going to be approaching 2 from the left and right. So if I'm approaching 2 from the left, that would be where x is less than 2. So I'll be using this function. And if I'm approaching 2 from the right, then I would be using the place where x is greater than 2. That would be this function. Okay. So direct substitution here. If I plug in 2, I get 2 squared, which is 4. 4 times negative 4, 1/4 is negative 1. Negative 1 take away 1 is negative 2. Here, if I plug in 2, I get cosine of pi over 2. Plug in 2 here, the 2 reduces with the 4 to make 2, right? So you're left with pi over 2. Cosine of pi over 2 is 0. And therefore 0 times 4 over pi is just going to be 0. So the final answer there is 0. Those are not equal. This is not continuous. Well, I guess on this one, a better way to write our final answer would be to state that the limit from the left is not equal to the limit from the right. There we go. And therefore, we don't need to do this. We're going to say it's not differentiable either, because it's not possible for a function to be differentiable if it's not continuous. So we're going to say it's not differentiable since f of x is not continuous at x equals 2. So let's move along. Okay, it's kind of a similar question, but instead of asking if they are differentiable or continuous, it's asking us to make it continuous and differentiable. So to do that, the first thing that we do is we, once again, same approach. We're going to be approaching 2 from the left, and we're going to be approaching 2 from the right, and we want them to be equal. Okay, so if I'm approaching 2 from the left, then I'm going to be using the piece that has the ln in it. And if I'm approaching 2 from the right, I'm going to be using the piece that has the square root in it. So if we do our direct substitution, if I plug in 2 here, 2 squared is 4, and 4 take away 3 is 1, and ln of 1 is 0. Here, direct substitution, 2 times 2 is 4, 4 take away 3 is 1, the square root of 1 is 1, and a times 1 would be a, plus, plug in your 2 here as well, and you get 2b. So, in order for this thing to be continuous, a plus 2b would have to come out to equal 0. Now, we also want to make sure that it's differentiable. So to do that, we need to find our derivative. So to take the derivative ln, you always do the inside on the bottom and the derivative of the inside on the top. To take the derivative of a square root, you put that square root on the bottom, put the derivative of the square root inside the square root on the top, so the derivative of the inside there is 2. The a in the front stays on the top. It's not part of the process, so it just stays in the numerator. And you always have a 2 on the bottom whenever you do a derivative of square root. In this case, they go away, so we don't really need the 2's. Plus bx. Now the derivative of bx is just going to be b. Oh, I put the wrong number. These are 2's. Okay, so in order for it to be differentiable then, as I approach 2 from the left, and as I approach 2 from the right on this derivative function, they should come out equal. So, I'm approaching 2 from the left, I'll use the top piece. I keep making this a plus, it's a minus. And if I approach 2 from the right, then I'm going to be using the bottom piece. Let's do some direct sub. So if I plug in 2 to the top, I get 4. If I plug in 2 to the bottom, I get 4 minus 3, which is 1. So 4 over 1 is 4. And if I plug in 2 here, 2 times 2 is 4, minus 3 is 1, and the square root of 1 is 1. Therefore, a over 1 is just a, and then b doesn't change. There's no x there. At that point, we have a system of equations that we need to solve. So we take the criteria that we needed for it to be continuous, is that a plus 2b had to be 0, and we put that with the criteria for differentiability, which is that a plus b has to make 4, and we solve the system of equations. You can use substitution or elimination. I feel like this one's set up pretty nicely for elimination. So I'm going to multiply the bottom by a negative. If I do that, that becomes a negative 4. That becomes a negative a, and that becomes a negative b. Adding straight down, we get negative 4. The a's go away, and 2b take away 1b is b. And so there's b. Now we need to find the other letter, a. So to do that, you just take one of your original equations, and you replace the b with the answer that you got. It's negative 4. And there's your answer. All right, next problem. Okay, the graph of f is given below. Determine if the function is continuous and if it is differentiable at each point, and give a reason for your answer. All right, so we're going to start off with x equals -4. That would be right here. Now we already know the answer just by looking. We should understand that it's continuous but not differentiable. It's continuous because there's no holes, gaps, or jumps. It's not differentiable because there's a cusp. But we have to know how to write that, okay? So that matters. So on part A, we're going to say it is continuous. And the reason for that is because the limit as x approaches -4 is the same thing as f of -4. Okay, that's how you would express the reasoning for why it's continuous. And we're going to say that it's not differentiable. And it's not differentiable because the slope from the left is not the same as the slope from the right. And the way that you write that is in this fashion. Okay, so that's the answer to part A. Okay, part B, -2. At -2, it's not continuous. You can't have a hole there. So, but you have to know how to say why it's not continuous there. So we're going to say not continuous. The reason why is because the function is not defined there. F of 2 does not exist or is undefined. Okay, and we're going to say not differentiable because it's not continuous. Okay, let's take a look at 0. At 0, we have no holes, gaps, or jumps, no cusps, so it's continuous and differentiable. So for part C, we would say it's continuous because the limit as x approaches 0 for the function is the same thing as the function's value at that point. And we would say that it's differentiable for the same reason, but just with the derivative. The limit as we approach 0 for the derivative function is equal to the slope of the derivative at that point. So there's that. All right, number 2. X equals 2. Okay, so that's not continuous. So the reason that's not continuous is because the limit from the left is not the same thing as the limit from the right. So since we're going to say it's not continuous, since the limit as we approach 2 from the left is not the same thing as the limit as we approach 2 from the right. And we're going to say it's not differentiable since it's not continuous. All right, x equals 4. For x equals 4, let me bring back this answer because I'm going to use some of that again actually. For x equals 4, it's not continuous. The limit exists, because as I approach 4 on the left and right, they're both approaching the same x value of 1. But the problem is that the function's value at that point is -2. They're not the same thing. So the limit is not equal to the function's value. So we're going to say not continuous because of this. And we're going to say it's not differentiable since it's not continuous. Same answer. Last one, number 6. It's asked, or sorry, letter F is asking, is it continuous at 6? There is no x value here at 6 because that's an asymptote. So that means that, once again, it's not continuous because f of 6 does not exist. And since it's not continuous, once again, it's not differentiable at 6. Part G asks us, for which values of x is the function differentiable but not continuous? That's impossible. I don't even need to look at the graph to answer that. It's not possible for a function to be differentiable if it's not continuous. So that's kind of like I guess you could say it's like a trick question, if you will, but make sure you're aware of it. H, for which values of x is f of x continuous but not differentiable? Now that's possible. It's possible for a function to be continuous but not differentiable. The only one up here is right here. Continuous means there's no holes, gaps, or jumps. So the answer to H is x equals 4, negative 4. On the day we did this lesson, there is another time when that could happen. It's not on this graph, but if you ever have a graph with a vertical tangent line, like right here, for instance, that's an undefined slope, but it's not a discontinuous point. So that would be another time whenever it is continuous, but not differentiable. All right. Particle moves along a horizontal line. Its position function is s of t for all t greater than or equal to 0. For each problem, find the position, velocity, and acceleration at the given value of t. So this is my position function. My velocity function would be negative 3t squared plus 2t plus 56. And my acceleration function would be negative 6t plus 2. And we're going to find out what each one of these things is at 2. So s of 2, plugging that in, we get 2, not negative 2. We end up here with negative 8, 4, and gosh, 112. The heck is that going to be? So that's a negative 4 from 12 is going to be 108. As for this one, s prime of 2, and plug 2 into this thing now. Exponents are first, guys. So that's 4. We got negative 12, 4, and 56. So that makes negative 8. If I take 8 away from 56, I'm going to be left with 48. It doesn't look like they're giving me any units, by the way, so I don't really need to worry about that too much, but just know that this is my position, this is my velocity. Lastly, we need to do our acceleration. So we're going to be plugging 2 into the acceleration function. That's negative 12 plus 2, which is negative 10. There you go. Velocity, acceleration, and position. The next question asks us, which direction is this particle moving in? Since the velocity is positive, it's moving left, because I believe it was a horizontal axis, if I'm not mistaken. So let's go back and see. Yeah, we're moving along a horizontal axis, so it could be going left or right. And since the velocity is positive, it's moving, not left, it's moving right. Sorry about that. Moving right. So the next question is the particle in question 10 speeding up or slowing down? To answer that question, you compare the acceleration with the velocity. Since they're opposite signs, this would be a slowing down problem. I'm not going to do this one. That's just repetitive, but if you want more practice, there it is. So I'll skip those questions there. All right, let's the fun begin. We're going to talk about some related rates here. Spherical snowball. It's rolled in fresh snow, causing it to grow so that its radius increases at a rate of 3 inches per second. How fast is the volume of the snowball increasing when the radius is 3 inches? So we want to find how fast the volume is increasing, and that's going to be in cubic inches per second. They give us the rate of change of the radius as 3 inches per second, and it's positive because it's increasing. So we're looking for a formula with respect to a sphere. that connects the volume to the radius. The volume of a sphere is this. I will give you these formulas on the test if you ask me for them. It's not going to be printed on the test, but I will give them to you because that's what they do on the AP test. Okay. After you have your formula, you take the derivative of that thing. So the derivative of v with respect to t is just written symbolically like this. Over here we have a constant. Those two things are constants, so they're just going to sit there. They're not going to change. But the r we do need to apply the derivative to. We're going to take the derivative of r cubed, so we move the 3 to the front, and we take 1 off the power. Those 3's cancel, and don't forget chain rule with implicit differentiation gives us a dr dt. So here's my derivative formula. And now we're ready to start plugging stuff in. So I want to find out what this is, and to do that I need to have two things. I need r and I need dr dt, both of which we have. We want to find how fast the volume is increasing when the radius is 3, so that's what I'm plugging for r. And we also need to plug in the dr dt, which is also 3. So if I plug those in, this is going to end up being 27 times 4. What's that going to be? 108, I believe. 108 pi cubic inches per second. Final answer. Moving on. Cubes. We got a cube that's shrinking. Cubes have all edges of same length, so we'll call them S. It says the sides are decreasing at a rate of 4 meters per minute. And what is the rate of change of the volume when the sides are 6? So we're looking for, once again, the rate of change of the volume, and that's going to be in cubic meters per minute. Now, since this thing is decreasing, whatever the answer is, it needs to be negative in the end. It will be. But we also need to find the given rate, which is the side lengths. So the rate of change of the side lengths with respect to time, they say, is 4 meters per minute. But since it's shrinking, it's going to be negative 4 meters per minute. Now we need to find a formula for cubes that connects volume to side length. The volume of a cube is given by the sides cubed. So if I take the derivative of this with respect to t, I get dv dt, 3s squared, ds dt. All right. We don't know dv dt. That's what we're trying to find. We do know s. We want to find the rate of change of the volume when s is 6. So I'm going to put a 6 in there. And I also know ds dt, which is negative 4. Okay, so let's see what we got here. I've got pretty big numbers to deal with. 3 times 36 times negative 4. That's going to be negative 12 times 36. I'm going to get my calculator. Looks like 432. Okay. All right, next question. Another circle problem. A crowd gathers around a movie star. Looks like a pentagram. That's not good. Oh well. Forming a circle. The area taken up by the crowd increases at a rate of 49 square feet per second. How fast is the radius increasing? So we have a radius here. They are asking us to find what is dr dt. Radius is just a length measurement, so it's going to be in feet per second. And it's increasing, so we would expect a positive answer. They tell us that the area is increasing at a rate of 49 pi square feet per second. So we need to find a formula that connects radius to area, and that would be area equals pi r squared. We would take the derivative of this, get dA dt. Pi stays there, 2 to the front, take 1 off the power, dr dt. Now what we're looking for is dr dt, so that means we need to know what r is and we need to know what dA dt is. R is going to be 13 feet and dA dt is going to be 49 pi. So let's plug those things in. So the pi just goes away. This is 26, and then you would divide it on both sides. So you end up with 49 over 26. And we don't want to forget our units. It was inches, no, it was feet per second. I don't think that reduces, so we're good. Okay, next one, we got a square this time. Square is growing so that the length of its diagonals are increasing at a rate of 4 meters per minute. This is we didn't do any questions like this in class, so I'll go ahead and work it out just to kind of expose you guys to something like this, but I don't plan on putting something like this on your test just because we didn't go over it, but that's just me being nice because I know that these questions are a little bit hard, but I do want to make sure you guys are ready for it, so I'd like to discuss it because eventually, you know, we kind of need you guys to get to a place where you can do a variety of these types of questions. So we're talking about a square with a diagonal. They're telling us that we want to find how fast is the area increasing. The units for that are going to be in square meters per minute. But they tell us the rate at which the diagonal is increasing, which is in 4 meters per minute. All right. So here's the thing. We don't know what these sides are here. Okay, but the thing is we need those sides. Because the area of a square is sides squared, right? But I don't want S in my formula. I want A and D. So how am I going to get rid of this S? Well, we have to do a little bit of an extra work here. So what is the relationship here between D and S? Hopefully you guys might be thinking maybe Pythagorean Theorem. S squared and S squared makes 2S squared. Now let's get S by itself. Ready? I'm going to divide both sides by 2. And then I'm going to square root both sides. So S is equal to D over the square root of 2. Why did I do that? Well, remember, I don't want A and S, I want A and D. Well, now that I know that S equals this, I can replace the S with D over the square root of 2. Now I have a formula that has the two variables that I care about in it. So, first of all, let's simplify it. It comes out to be D squared over 2 if you distribute your power there. The 2 makes the D a D squared, and this 2 makes the square root of normal 2. Next, we're going to take the derivative of it. And from here on out, the problem's really not that much different than the things that we've been doing all along. If I take the derivative of this, you might want to think of this d squared over 2 as 1/2 d squared, if that helps at all. That way, when we take the power rule, you move it to the front, right? You get 2 over 2, which is 1. And then you take a power off of the 2, which makes it 1 d to the first power. But don't forget your derivative afterwards, the chain rule. All right. So now we've got that, and we're being asked to find out what is dA dt. So to get that answer, I need these two things. I need d. The diagonals are 5 meters each, so there's that. d dt is going to be 4 meters per minute. And so as you guys can see, the answer is going to be 5 times 4, which is 20, and that's going to be in square meters per minute. All right, moving along. A 10-foot ladder is leaning against a wall and sliding towards the floor. The foot of the ladder is sliding away from the base of the wall at a rate of 3 meters per second. I'll call this B for the base. How fast is the top of the ladder sliding down the wall? We'll call this W for wall, when the top of the ladder is 6 feet from the ground. So the ladder itself is 10 feet long, and that's not going to change, so I put a number there. The rate that they give us is how fast the base is moving away, so that would be dB dt, and they tell us that that rate is 3 feet per second. The rate that they want us to find is how fast the ladder is sliding down the wall, so we're looking for dW dt. Yeah, Chris. Oops. Yeah, I think so, yeah. Somebody just left it in. It's been there for a few days. So since it's sliding down the wall, the W is going to be shorter. We're going to expect this answer to come out negative. We don't really need to force it. It's going to happen naturally, but just know we should end up with a negative here in the end. Okay, so I'm looking for a formula that connects B to W. And I can do that if I use the Pythagorean Theorem. Oh. Okay, so this is just 100. And now I'm going to go ahead and take the derivative of this thing here. So if you take the derivative of W squared, you put the 2 in front of the W, multiply it by dW dt. Same thing with the B. And then finally, derivative of 100 is just 0. So what I'm looking for once again in this problem is dW dt. So we need a few things. We need W, we need B, we need dB dt. We've got dB dt, it's 3. B, I don't think they gave that to us. It says here that the ladder is 6 feet away from the ground. That's talking about W. So we know W is 6, but we don't know what B is yet. And as I mentioned before, when you don't know what one of your pieces are, a lot of times you're going to come back to your original problem before you took the derivative of it. You're going to solve for it. So W is 6. That's 36. Taking the square root on both sides, we get 8. So now I know that this is 8, and we're ready to go ahead and plug everything in and get our final answer. So I'm going to plug in 6 here, 8 here, and 3 here. minus the 48 on both sides and divide by 12, you're going to end up with negative 4, and that's going to be in feet.
All right, so number 21. A particle is moving along a horizontal axis according to the position function s. It's measured in inches, and time is measured in seconds. Part A is asking us to find the average velocity on the interval of 0 to 2. So average velocity is given by the formula s of time 1 minus s of time 2 over time 1 minus time 2. And these are our times. So I need to start by finding the position at 2 and the position at 0. So let's do that. So s of 2 is equal to our little formula they gave us, negative t squared plus 18t minus 80, and we're going to be plugging in 2. So we have negative 4 plus 36 minus 80. Getting negative 48 for that. Next we have s of 0. And these are just going to go away, leaving with negative 80. So s of 2 we decided was negative 48. S of 0 was negative 80. And then we have 2 minus 0 on the bottom. And we'll go ahead and simplify that. The double negatives here on the top become positives. And that's going to leave me with 32 over 2, which is 16. Now we want to get our units out of this. The top numbers, negative 48 and 80, those are s values. That's the position, and position is measured in inches. So these are inches on top. And these values on the bottom, these are the time values, which is measured in seconds. So we have inches per second as our units there. And so that would be the average velocity of this particle on the interval from 0 to 2. Let's go ahead and take a look at part B. Part B asks us to find s prime of t, which means we want to find the derivative of the function s up there. So just applying the power rule, the derivative of that is going to be negative 2t, and the derivative of that is 18. And the derivative of a position function represents a velocity function. And to be more specific, an instantaneous velocity function. So that would be the answer to part B. Part C. The answer from part A would be a good estimate for which of the following. All right, so just as a quick side note, we did some FRQs last weekend where I gave you a table, and we could use an average rate to estimate an instantaneous rate. Okay, so just as a quick example before we begin answering part C, so you don't need to write this, this is just to kind of refresh your mind. If I told you this is x and this is f of x, and I give you a couple of x values here, and a couple of y values that go with them. All right, and I was to ask you to estimate f prime of 4, what would you do? Well, this is an instantaneous rate of change, but we can't do that from a table, but we can estimate an instantaneous rate of change by doing an average rate of change with the two values that are closest to the number they give us. They give us 4. The two numbers that are closest to that are 5 and 3. So we could do an average velocity on this interval to give me an estimate of 4. So coming back then to this problem, it says for part C, it says the answer from part A would be a good estimate for which of the following. Well, what two time values did they give us? They gave us the time values of 0 and 2. Okay, so which of these has an input that is close to 0 and 2? Well, that would be this one. So the average velocity on the interval from 0 to 2 would be pretty close to the instantaneous velocity at 1. Okay? All right, let's go ahead and move on to part C. Evaluate and interpret the expression s prime of 2 minus s prime of negative 2 in the context of this problem. Well, now, the first thing that you want to take note of is the interval. Okay, so what is the interval? It looks like we're going from negative 2 to positive 2. Now, this is a setup for an average. So this is an average of something. But an average of what? Well, if you look at your, it's an average rate of change. Well, I won't put rate of change yet. If you look at your notes, I believe it's in lesson 4.7 or 4.8, one of those two. If these were just s's, then this would be an average velocity. But if it's an s prime, this is an average acceleration. So then we want to evaluate and interpret this expression in the context of the problem. So we kind of already have our interpretation of what the answer is going to be, but we don't know what the answer is yet. So I'm going to go ahead and write interpretation up here first. Whatever the answer is, it's going to represent the average acceleration of the particle on the interval negative 2 to 2 seconds. Now remember, an interpretation should include your input units, the context, and the output units. We'll get those output units in just a minute, but for now, that's the interpretation. So let's go ahead and actually figure out the solution of this. Now, we already know from part B that s prime of t is equal to negative 2t plus 18, right? Now, I want to figure out what's s prime of 2, so I would just plug 2 in there, which is going to give me 14. And then we also want to find out s prime of negative 2. So we'll be plugging negative 2 in there. And that's 22. So replacing these values here with the values we just calculated, we would have 14 minus 22 over 2 minus negative 2, which is 4. And that's going to be 14 minus 22 is negative 8 over 4, which is negative 2. And now we want to figure out the units. What are the units for this? Well, s prime is a velocity, and velocity is going to be in inches per second. The bottom numbers are time values, so those are seconds. So we have inches per second, which is inches per second squared. Okay, so we could put up here, back up here in our interpretation, negative 2 inches per second squared is, and then we have the rest of our interpretation, is the average acceleration of the particle on the interval from negative 2 to 2 seconds. All right, let's move on to number 22. All right, given that f of x is equal to this, find the equation of the line tangent to the graph of f of x at x equals 1. As you guys know, we need to find the value of x, we need to find the value of y, and then we need to find the slope. The x is given to us. We want to find the equation of the line tangent to the graph at x equals 1. To find the y value, we need to plug 1 into the original function, which is going to be 1 over pi tangent of pi times 1 plus ln of 1. ln of 1 is 0. This is just going to be pi in here, so tangent of pi is also 0. And so we have 0 plus 0, which is 0. So my y value is 0. Let's find the m value. The m can be found by finding the derivative of f and plugging in the x value. All right, so we need to find the derivative of this thing up here. To find the derivative of f, the constant multiple stays there. It's not going to change. The derivative of tangent is secant squared. But we also need to multiply it by the derivative of the inside, which is pi. So I'll multiply it by pi out here. And then we have plus the derivative of ln of x is 1 over x. Now we can simplify and cancel those pi's out. And so we really just have this left. So we want to plug 1 into that. All right. So this is just pi. And secant is really just 1 over cosine. So we can write it like this. Now cosine of pi is -1, but we're squaring it, so it's +1. And 1 over 1 is 1, so we're left with 2 as our slope. So the equation of our tangent line would be y is equal to our slope times x minus the given x value plus the y value. And then if we just simplify, which if you have an FRQ, you don't really need to worry about simplifying it, but we have that there. So that would be the tangent line at x equals 1. Part B says use your answer to estimate f of 1.25. So for part B, I want to estimate what f of 1.25 is. F of 1.25 should be approximately the same thing as y of 1.25, where y is our tangent line, because tangent lines are close to the original function. So I'm going to take this equation over here, and I'm going to replace x with 1.25, and we're going to simplify from there. And there's our answer. So we're looking at approximately 0.5 for our estimation there. Go ahead and take a look at part C. If f of 1.25 is actually 0.541, the question is f concave up or down? Well, if f of 1.25 is 0.541 and our estimate was 0.5, that means that the actual value is greater than the estimate. Now, if the actual value of our function is greater than the estimate, that means our function is above our tangent line, which means that our function would have to be concave up. Okay, so now you may have an FRQ like this. You could just put since and then this. Since the actual value is greater than 0.5, it's concave up. That's good enough. You don't need to draw the picture like I did. I just did that to explain myself. But this is sufficient. You need to make the statement that the actual value is either greater than or less than the estimated value. All right, we have another one like that here. It's just kind of formatted a little bit differently. So we have if f of x equals y and f of 4 equals 7, and dy dx is equal to this, well, what can we do? Well, part A, find the equation of the line tangent to the graph of f at 4. Okay, so we need, for a tangent line, we need an x, we need a y, and we need an m. The x value is the one in the parentheses, and the y value is the one outside the parentheses. Now the slope is going to be the derivative of f. Now that's what this is right here. So the derivative of f, and you're going to plug the x value and y value in. So my x value is 4, my y value is 7. Half of 4 is 2, and 2 times 7 is 14. So as you guys can see, this problem is just different and yet it's also the same. We're really doing the same thing, but how they gave us the information is different. On the last problem, they just gave you a function, and you had to plug it into the y yourself, and then you had to find the derivative yourself. But on this problem, they're just telling you the y, and they're telling you the derivative. So it's actually easier than the last one, in my opinion. So to finish up part A, we need to write our tangent line. We have y is equal to the slope times the x value plus the y value over there. And then simplifying it would be that. So there's our tangent line. There's really not a whole lot different for the remainder of the problem, but I'll go ahead and go through it anyway. The rest of it's very similar to the last problem with pretty much no interesting twists or turns along the way. Use your answer to estimate f of 3.8. F of 3.8 should be approximately equal to y of 3.8, where y is my tangent line. I'll label it this time because we're using y here, but they're also saying the function itself is y, so that's a little bit confusing. I guess we can call this y1 just to be specific and make it separate from the original y there. So the original function's value at 3.8 is approximately equal to the tangent line's value at 3.8, which is 14 times 3.8 minus 49, which comes out to be, let me get my calculator, about 4.2. All right, last part, part C. If f of 3.8 actually equals 4.739, is my graph concave up or down? Well, since the actual value of f is 4.739, which is greater than my estimated value using my tangent line, that means my tangent line must be below the function once again, and just like on the last one, it turns out that that would be concave up. Okay? If you ever had a situation where the estimated value was greater than this one, then it would be concave down. So, but there it is. So hopefully that was helpful, and we'll see you guys on test day.